That was due.
I just would like you to feel that you should be doing that.
Start today.
Today. Preferably yesterday, but I'll settle for today.
Preferably like 2 weeks ago.
Yeah, work on that. Okay, so let's talk about dipoles. We talked about these a little bit earlier, but what is a dipole?
It's a thing with positive and negative. And
Yes,
spins.
positive and negative charges that are stuck together, and they can wiggle around, but they can't. The negative charges can't zoom off to the other side of a material, like in a conductor.
With a diode.
That's later. We can talk about diodes later. Not too much though, because we get our circuits in this class are real basic. It's like, ooh, a resistor. Here's more resistors. Also a battery, and then eventually we add a capacitor and inductor, and that's it. Okay, we don't talk about diodes or transistors. If you like any of that stuff, you're gonna take another class. Okay, we just venture into circuits. Don't worry, it'll be hard enough as it is. So here's a dipole. Okay, it's a positive charge and a negative charge. They're stuck together. They're a distance. We'll call it 2A apart. Okay, and this brings us to something called the electric dipole moment. All right, which sounds really fancy, but all it really means is it's a vector, which we call P for electric dipole moment. At least there is a P in there. So P for dipole. I don't know. It's directed from negative Q to positive Q, and you'll notice that's the opposite of which way the electric field would point. Because where do electric field lines point? From what to what? Positive to negative, right? They always start. Electric field lines start on positive charges and end on negative charges. Okay, they go in the direction a positive charge would move. All right, but the dipole moment points from negative to positive. So, and there's a reason for this, and we'll talk about it in a minute. So it just joins these charges, okay? And it's going to have a magnitude of 2 times the, so basically the distance between the charges times the positive charge. Okay, so 2AQ. All right, so there's our dipole moment, all right? And let me show you why we have this. So if you put a dipole in an electric field, so let's say here is a positive, just a constant electric field. Here's our dipole, okay? What's the force on this charge? Which way does it point?
Right.
Points to the right, okay? The force on this charge?
To the left.
To the left. If these charges are the same magnitude, what's the net force on this object?
0.
0, okay? So the net force is 0. But we do have something else going on. Let's say we fix it at the middle. Now what happens?
Yeah.
It spins. Why does it spin?
Because there's more positive than there's negative.
No.
The overall field is positive though, right?
We have 2 forces that cancel.
Yeah, that's the act of them canceling
So if
out.
our net force is 0, why does it move?
Oh, because that's torque.
Torque!
Hey.
Remember torque? You guys like torque? What's torque?
Force times power.
Force, not just times, it's a special times. Not cross. Force as a cross product of R. And what is R
There.
in torque?
Level R.
The distance from what to what?
From the fixed point.
The distance from the axis of rotation, meaning where does this thing pivot? So the pivot point to the force. Okay? So what's R in this case?
A.
A, right? Remember this is 2A. So R is A. We have a force F, and then we have to do a cross product. So is that sine or cosine of theta? Cross product? Sine. Dot product is cosine. Okay? So that means we're going to have 2, because there's 2 forces, times F. Right? So that's F cross R, which is A. Okay, so 2F sine theta A. Everybody okay with that? All right. So that's going to give us something like, so here's the number. 2F sine theta times A. Okay, Okay, so there's two of these forces because this comes from F cross R. Alright? And it's still a vector, but we're not going to worry too much about it. Although you can actually figure out the direction of the vector, right? It's going to be into the page. Okay, that's the way it's going to rotate. Because this thing's going to rotate like this, correct? Right? This force pulls this way, that pulls that way, and it should rotate until it lines up with the field. Alright? And so this is, so anyway, we know, because this is a constant E, we can rewrite this as 2AQ E sine of theta. And it's probably positive or negative. One of those. Okay? So if you just leave this thing in this field, it's going to rotate until it does that. Now realistically, it's probably going to go like, it's going to miss and go back and then oscillate, but let's just stick with this. Okay? So we have a net force of 0, but we do have torque. So this thing rotates. So the reason we do this dipole thing is because the dipole, even though it points sort of the opposite, so this points from positive to negative, so you can have a bunch of positive charges over here, a bunch of negative charges over here. This points from negative to positive. But remember, it's going to line up with the field. Dipoles always line up with the field. And we can write the torque as the dipole moment crossed with the electric field. You can actually pull this out, and you can see 2AQ. This is what we call the dipole moment. Okay? E is the electric field, and this sine theta indicates that this is a cross product. Okay? So P cross E gives you the torque on a dipole. Makes things a little bit simpler. The derivation's kind of ugly. Alright? If you want the energy, we won't go through the whole derivation, but you have to start with work, and then you do torque d theta, all right? If you want the energy, it's just the dot product, all right? That's actually the negative dot product. And what does this tell us? Let's look at what this actually gives us, okay? When you're right here, these two things are parallel. So what's your energy? Do you expect it to, so is this a high energy state?
No.
No. It should be your minimum energy because you're not storing any energy, you're not opposing what this thing wants to do. So the reason this negative's here is this is negative PE, right? Because the dot product is cosine. Cosine of 0 is 1. Yes, cosine of 0 is 1. Okay? So if you have this other configuration, this should be the maximum energy. Okay? This is the dot product of P and E, but now the angle between them isn't 0, it's 180, or pi. Cosine of pi is negative 1. Okay? Negative 1 times P times E is positive P. So that's the maximum value you can get. Everything else is in between, right? It's either greater than negative PE or less than positive PE. But what does this mean?
0.
0. Okay? Is 0 the minimum energy in this case? No, why? Because you can have negative. So this is 0, but it's not that meaningful. Okay? So basically, maximum energy is here. Minimum energy is here. Maximum energy is here. This is just in the middle. But that's how dot products work. Alright? So because these are a positive and negative charge stuck together, remember this is how insulators work. And this is going to be really important when we're going to start talking about capacitors and dielectrics in the next couple chapters. Insulators are something called dielectrics. That's how you make your capacitor work better. And it's kind of subtle, but what it does is, these things can wiggle, but they can't move a lot. And so you can change the configuration of charge within a material, just not to the extremes that a conductor would. Okay? And so this is going to end up playing a pretty big role when we start talking about capacitance, which is in 2 chapters. But